Okay. So yesterday we have seen 12 problems, right? So first 10 problems are based on an infinite abelian group. So they will give one set, they will give one binary operation. With that binary operation, we need to verify whether the set is group or not. And then we have seen two examples of finite group, which is cube root of unity and fourth root of unity. Now we are going to discuss another 4 problems now in the finite groups, and then I will give some exercise problems for you to practice, right? So first we are going to do 4 problems quickly now, right? So the first, the 13th problem is, prove that the set 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5 is a finite abelian group, is a finite abelian group. We need to prove this set is finite abelian group with respect to addition modulo 6. With respect to addition modulo 6, right? This is a new operation that we are dealing. So it is addition modulo 6. That means we need to add 2 elements. If that element is greater than or equal to 6, we need to write the remainder. So for example, if you add 4 plus 3, this is 7. So 7 is greater than or equal to 6. So you need to write the remainder. So when you divide 7 by 6, what you will have? You will have 1. So you have to write this as 1. So you need to write plus 6. For example, what will be 1 plus 4? It is 5. 5 is less than or equal to 6. So you don't need to rearrange, and you don't need to divide because 6 is less than or equal to 5. And again, what will be 3 plus 3? It will be 6, which will be 0, right? Because 6 is greater than or equal to 6, so we need to divide by 6, the remainder will be 0. That is what addition modulo. Addition means we need to add 2 elements, and then if that number is greater than or equal to 6, we need to write the remainder, right? Yes. So we need to prove that this is a finite abelian group of order 6. With respect finite abelian group of order 6. You can see there are 6 elements here. So order of a group is nothing but number of elements in the group. So we have 6 elements in the group. So order of this group is 6. So since order is a finite number, so therefore it is a finite abelian group. So before that, what you will do is, whenever we have a finite group, it is always advised to make a K-list table. So here 0, 1, 2, 3, 4, 5, and again 0, 1, 2, 3, 4, 5. The operation is addition modulo 6. So plus and in suffix you need to write 6. So you need to add. So 0 plus 0 is 1. You can straight away write those elements because 0 plus 0 is 0, 0 plus 1 is 1. Because 1 is 0 is our ideal element here. So 1 plus 0 is again 1. This will be same. So 1 plus 1 is 2, right? 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. 1 plus 6 is 6. Sorry, 1 plus 5 is 6. 6 is greater than or equal to 6. So you need to write the remainder. So it will be 0. 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3 is 5. 2 plus 4 is 6. So 6 you have to write 0. 2 plus 5 is 7. 7, the remainder will be 1 when you divide by 6. 3 plus 1 is 4. 3 plus 2 is 5. 3 plus 3 is 6, which will be 0. 3 plus 4 is 7, which will be 1. 3 plus 5 is 8. So 8 divided by 6, remainder will be 2. 4 plus 1 is 5. 4 plus 2 is 6. That means remainder will be 0. 4 plus 3 is 7. Remainder will be 1. 4 plus 4 is 8. Remainder will be 2. 4 plus 5 is 9. Remainder will be 3. So 5 plus 1 is 6. Remainder will be 0. 5 plus 2 is 7. Remainder is 1. 5 plus 3 is 8. Remainder is 2. Remember, we are dividing by 6. 5 plus 4 is 9. 9 mod 6 is 3. 5 plus 5 is 10. This will be 4. That's it. Now we need to check all the properties. So first is closure. So just you can see whatever elements you take, there is all the elements belongs to the set 0, 1, 2, 3, 4, 5. So whatever element you take, if you want to take 4 and 3, so 4 mod 6, 3 is 1. So 1 also in the set. So it is clearly closed, right? Because you can see every element here belongs to the set G. So you can also write, you can arbitrarily take two elements, or you can just say every element in Cayley's table, belongs to let us say this set is G, belongs to G. So therefore it is closed, or you just take arbitrarily two elements, you just find a plus B mod 6, surely that element will also be in G. Associative, again it will be associative, right? So for example, let us take three elements, let us take 1, 2, 4 belongs to G. So we need to verify 1 plus 2 plus 4 is same as 1 plus 2 plus 4, the operation is plus 6. So this will be 1 plus 6, so 2 plus 4 is 6, 6 mod 6 is 0, right? So 2 plus 4, so you can say 2 plus 4 is 0. And again here 1 plus 2 is 3, 3 mod 6 again 3 plus 4. So again this is 1, 1 plus 0 is 1, 1 mod 6 is 1 again, and this is 7, 7 mod 6 is 1. So you can see it is associative. So what is the ID element here? So clearly 0 belongs to G, 0 is the ID element. You can see 0 plus some element plus something have to give me the same element again. So therefore 0 is our ID element, 0 belongs to G is the ID element. So for finite group you need to find inverse for single element. So inverse for 0, 1, 2, 3, 4, 5. So what is the inverse for 0? So you just see where 0 is in the corresponding row. So 0, you need to add some element to get E. E is 0, right? E is 0. So therefore inverse of 0 is 0. So again we are getting 0 here. So inverse of 1 is 5. That means 1 plus 5 will give you ID element. Inverse for 2 is 4. Right? Inverse for 2 is 4. Inverse for 3 is 3. That means this means 1 plus 6, this will be 0. That is 2 plus addition modulo 6 plus 4 will be 0. That means with 2 you need to add 4 to get 0, because E is 0 here. So what is the inverse for 3? Inverse for 3 is 3. Inverse for 4 is 2, and inverse for 5 is 1. So you can see 1 and 5 are self inverse, and 2 and 4 are self inverse. That's it. So we'll do one more problem. It is also an abelian group, right? So they have said we need to show that it is a finite abelian group. So you need to show commutative, and again you can see 2 into 1 is 3 is same as 1 into 2. So it is commutative, right? Yes. So 14th problem, prove that the set 1, 2, 3, 4, 5, 6 is a finite abelian group. It's a finite abelian group with respect to multiplication modulo 7. So we need to show that this is a group with respect to multiplication modulo 7. So again here the operation is A into B, it is multiplication, right? So we need to multiply, that is AB mod 7. In the previous operation we have a plus 6b. This is a plus b mod 6. Here we have a so here the operation is AB mod 7. So here the operation is we need to multiply the element and we have to write the remainder when divided by 7. So you can see the set is 0, 1, 2, 3, 4, 5, sorry 1, 2, 3, 4, 5, 6. So here it is dot 7. So in the previous problem we have plus 6, here we have dot 7. So 1, 2, 3, 4, 5, 6 and this is 1, 2, 3, 4, 5, 6. Now 1 into 1 is 1, 1 into 2 is 2, 1 into 3 is 3, 1 into 4 is 4, 1 into 5 is 5, 1 into 6 is 6. Remember multiplication mod 7. In this. So 2 into 2 is 4, 2 into 3 is 6, 2 4s are 8. So 8 mod 7 will be 1. 2 5s are 10, 10 mod 7 is 3. 2 6 are 12, 12 mod 7 is 5. Right, so 12 mod 7 means 12 mod 7. So you need to write the remainder. So 7 divided by 12. So answer 7, remainder 5. 3 into 2 is 6. So 6 is less than or equal to 7. So you can keep that as it is. 3 into 3 is 9. So 9 mod 7 is 2. 3 4s are 12, which is 5. 3 5s are 15, which is 1. Right? Because when you divide by 15, you will have 14, remainder 1. 3 6 are 18. So 18 will be 4. 4 2s are 8, 1, 4 3s are 12, 5, 4 4s are 16, 2, 4 5s are 26, 4 6 are 24, that means 3. 5 2s are 10, it means 3, 5 3s are 15, 1, 5 4s are 26, 25, 25 will be 4 because we are 21, so these are 21, so remainder will be 4. 30 will be 2 because 5 4s are 28, sorry 7 4s are 28, so remainder will have 2. 6 2s are 12, so we have 5. 6 3s are 18, so we have 4. 6 4s are 24, we have 3. 6 5s are 30, we have 2. 6 6 are 36, we have 1 because we have 35. 7 5s are 35. So again you can see every element in Cayley's table belongs to G, so therefore it is closed. And again you can see it is associative also. You just take randomly 3 elements, it will be saved. And you can see 1 is our ID element. So 1 is our ID element. So what is the inverse for 1? The inverse for 1 is 1. Inverse for 2 is 4. Inverse for 3 is 5. Inverse for 4 is 2. Inverse for 5 is 3. Inverse for 6 is 6. That's it. And also abelian group because it is commutative. So A into B is same as B into A. You can see 3 into 5 is 1. 5 into 3 is also 1. 4 into 4 is 2. 3 into 2 is 1. 2 into 3. 3 into 2 is, it is 0, right? 3 into 2 is 6. Wait. 6. So we have mod 7, right? So 3 into 2 is 6. 2 into 3 is 6 again. So therefore, this is an finite abelian group. Why I am using finite? Because this set is finite. With respect to multiplication modulo 7. So 15th problem. Show that the set of 4 transformations, z minus z, so f1 of z is z, f2 of z is minus z, f3 of z is 1 by z minus 1 by z, so 1 by z, and f4 of z is minus 1 by z is a finite abelian group, is a finite abelian group with respect to composition. This is the first time we are facing composition, right? So the operation is composition, that is f star g is equal to f composite g. F star g is equal to f composite g. So f star g will be f composite g. Okay. So you can see the elements are f1, f2, f3, f4. So we have 3 elements. So we will have, so here we will write a circle. The circle denotes the composition. So this is f1, f2, f3, f4. This is T compositive. Okay. So f1, f2, f3, f4, f1, f2, f3, f4. So what will be my f1 composite f1? Surely f1 is ID element. You can see z. So you can see, you can right away write this table. So what will be my f2 composite f2? So f2 composite f2. So it is f2 of z. So f2 of z is minus z. So in f2 of z you have to replace z by minus z. So it will be minus half minus z. So which is z. So which is f1. So I know, I'm assuming that you know how to composite two functions, right? So it is f2 of this is f2 of z. So f2 of z is given minus z. So in f2 of z we have to replace z by minus z. So f2 of z is minus z. Here we have f2 of minus z. So we have to replace z by minus z. So it will be minus half minus z. So which is z, f1. So what will be my f2 composite f3? So f2 composite f3 will be f3 of f2 of f3 of z. F3 of z is f3 of z. So f3 of z is 1 by z, and this is, so in f3 of z we have, in f2 we have to replace z by 1 by z. So what is f2 of z is minus z. So it will be minus 1 by z, which is f4. So you can see only element that left is f3. So you can close your eyes and write the element f3. Or else you can also, and the important thing is you need to show all the calculations in the exam, right? So you need to show all 16 calculations. So f3 composite f2. So f3 f2. So f3 of f2 is minus z. So in f3 you have to replace z by minus z. So it will be minus 1 by z, which is f4. This is f4. And f3 f3. So f3 of z. So f3 of z is 1 by z. So in f3 we have to replace z by 1 by z. So this will be 1 by z, which is z, which is f1. So we can straight away write f2 here. And f4 composite f2. So f4 of f2 is minus z. So in f4 you have to replace z by minus z. So this will be minus 1 by z, which is plus 1 by z, which is f3. Now we can see in the column f2 is missing, in this column f1 is missing. So this is our K-list table. So and the important thing is you need to write all the calculations that I have erased. So as again you can see it is closed, and again it is also associative, because you can see every element in the K-list table belongs to the set. So therefore this will be closed. Our set is G is f1, f2, f3, f4, and f1 is defined like this, f2 is defined like this. So associative again. So what will be my ID element? f1 is the ID element, that is f1 of z is equal to z is the ID element, because you can see f1 into something, you have to give me f1 again, which is f1. f2 into something giving f2, that means f1 is again f1. So therefore f1 of z is our id element. So what is the inverse? You need to find inverse for every element. So inverse for f1, f2, f3, f4. You can see inverse for f1 is f1, and inverse for f2 is f2, and inverse for f3 is f3, and inverse for f4 is f4. Own inverse, right? Every element is own inverse. So I'll give you one problem for you to exercise. So I'll give you one problem for exercise. So 16th is show that the set of 6 transformations, 6 transformations, f1 of z is equal to z, f2 of z is equal to minus z, f3 of z is equal to z by z minus 1, f4 of z is equal to z by z minus 1, so z minus z, I'll verify the question. Sorry, this is z 1 by z, and f3 of z is 1 minus z, f4 of z is z by z minus 1, z by z minus 1, f5 of z. So f5 of z is 1 by 1 minus z, and f6 of z is z minus 1 by z. So you need to show that it is a finite abelian group of order 6. So same thing, in the previous problem we have f1, f2, f3, f4. So here we have 2 rows and 2 columns extra. So again you need to find the permutation. For example, what will be f3 composite f4? So just for your understanding, so it will be f3 of f4. So f4 is z by z minus 1. So in f3 you have to replace z by z minus 1. So f3 is 1 minus z. So you have to replace z by z minus 1. So f3 is 1 minus z. So this will be, when you simplify this will be z minus 1 minus z by z minus 1. This z will get cancelled. So we have minus 1 by z minus 1. This I can write this as 1 by 1 minus z, which is f5. So in every way like this you need to find the Cayley's table, and with the Cayley's table you can say that it is closed because every element of Cayley's table belongs to G, and it is associative, and f1 of z is the f1 of z is our id element, and you find inverse for which you get one answer, f1 as an answer. So last problem I am going to do in this topic, that is 17th problem. So show that the 4 matrices forms a multiplicative group. 16 or 17? 17. Show that the set of 4 matrices form a multiplicative group. Form a multiplicative group 1 0 0 1 and minus 1 0 0 minus 1 minus 1 0 1 and 1 0 0 minus 1 and minus 1 0 0 minus 1. So we need to show that these 4 matrices forms an multiplicative group. So let us name this matrix to be E, let us name this matrix to be B, let us name this matrix to be C. So now we will find the Cayley's table. So here the operation is normal multiplication. So this will be E, A, B, C, and again this will be E, A, B, C. So again I can see this is ID matrix, right? So when you multiply with any matrix, you get the same matrix again. So we can write this E, A, B, C, E, A, B, C. And what will be A into A? So A into A is nothing but A is minus 1, 0, 0, minus 1, minus 1, 0, 0, 1. This is normal matrix multiplication. So minus 1 into 1, minus 1 into minus 1 is 1. So 1 plus 0, this will be 0, this will be 0, and 0, this will be 1, which is E. Or let us say it is I, you can also write I, no, this will be E. So similarly you find A into B. So A into B will be, A is minus 1, 0, 1, and B is 1, 0, 0, minus 1. So in multiplex matrix you will have minus 1, 0, this is minus 1, so which is C. So this is C, the element which is left is B. So similarly you can fill up all the Cayley's table, and you can see E is our ID element, and inverse for E is E, inverse for A is A, and you find and you check where you are getting E in B, that will be the inverse. I'll send you some exercise problems, so you can refer page number 76, right? So in modern algebra Krishna series, you can refer page number 76 and 75 for exercise problems, right? I have solved some exercise problems, so I think you can do any problem. So if you have any doubt, you can text in Telegram. Page number 75 and 76 are the exercise problems for you, right? Yes. So I have solved 17 problems. I think this is more than enough. So they will give one set, they will give a binary operation. You need to show whether it is a group or not. That is the one we are talking about, right? So that's it. We are going on to the next topic, which is permutations. So in permutation, there won't be any theorem again. So again, it is based on problems. So after permutation, we will be solving only theorems. So the first two topics. The first topic is that we have finished. And second topic is permutation. So we don't have any theorems, only problems. So in UPSC point of view also there will be only problems. So from next topic, that is order of an element, normal subgroup, etc., we will have only theorems. So we are going to discuss permutation group, very important. We will have one 3 mark or 6 mark from this topic. So permutations. Permutations are symmetric group. Both are same. So permutation are symmetric group. So suppose if we have a set S. Suppose if we have a set S of natural numbers. Now you collect all one-to-one mapping. You collect all one-to-one mapping from this set S, right? A set of all one-to-one mapping. So I am going to call a set A of S, and this A of S denote the set of all one-to-one mapping on S. Then this set forms a group. Right? I'll give an example. Don't worry. A set of all one-to-one mapping on S. Then this A of S forms a group, and the order, number of elements in the group is, number of elements will be n factorial, right? N factorial. So I'll give an example for this. So this is a set of all one-to-one mapping on this set forms a group, and the number of elements in that set A of S will be n factorial. So first I'll give you an example. Before that, we will quickly recall what is meant by one-to-one. right? So when a function will be 1 to 1. So a function will be 1 to 1 if every element of A has a unique image in B, has a unique image in B, that is f of A is equal to f of B implies A is equal to B. That means, so suppose if this element is mapped to 0, this element cannot be mapped to this element again. So every element in codomain has only one pre-image in domain. This is not 1 to 1. You can see this element has two pre-images. Same element has two pre-images. So every element should have only one pre-image in the codomain. Right? Every element should have only one pre-image. You can suppose if this happens, then say this is not 1 to 1. So the question is, how many 1 to 1 mapping you can define if you have a set of n elements. This is very basic, right? This result comes from the school level. So for example, let us fix n is equal to 3. So we are going to call that as S3, right? Or this is same as Sn. So Sn is symmetric group of order n, is nothing but set of all 1 to 1 mapping on S, and that forms a group with number of elements is n factorial. So every element of A has a unique image in B. So first we will, let us fix n is equal to 3. So if n is equal to 3, so S3. So what is the set? The set is 0, 1, 2, sorry, 1, 2, 3. 1, 2, 3. This is our set. So we need to find all 1 to 1 mapping F from A to A. Let us call this at A. Set of all 1 to 1 mapping from this set to itself, right? A to A on A. So we need to find all 1 to 1 mapping between both sets. So A is 1, 2, 3. A is 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. So take me 10 seconds, I will fill the ink. Now how many 1 to 1 mapping you can define now? So you can see ID element is always 1 to 1 mapping. So this mapping is always 1 to 1. So we know that the ID element is always 1 to 1. So I can also define a map, 1 goes to 2, 2 goes to 3, 3 goes to 1. This is 1 to 1, right? So in this map I have transferred 1 to 2. Now what I am going to do is I am going to transfer 1 to 3 and 2 to 1, 3 to 2. Right, I'm here I left one position, so that means I left one position from here. Here I am lefting two positions, so 1 2 left 3, right? So here 3 1 left 2, so mapping 2 to 1 and this. So what are the 1 to 1 map? Another 1 to 1 mapping I can define from these sets. I can fix one is fixed. I can interchange these two. I can fix 2. I can interchange these two. I can fix 3, I can interchange these two. So these are the possible one-to-one mapping between these two sets. There is no other one-to-one mapping from this set, right? So one-to-one mapping is here, from here we should have only one pre-image, right? So no other mapping you can define. So you can see how many mappings here, 1, 2, 3, 4, 5, 6. So that's why, so we have 6 mappings here, and we can represent this in two ways. So first representation is very important concept. The first representation is, so you just write all the 6 possible elements. So you just write 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3. So you can see in the first mapping 1 goes to 1. So 1 goes to 1, 2 goes to 2, 3 goes to 3. Right, everything is fixed. Here you can see 1 goes to 2, 2 goes to 3, 3 goes to 1. Right, in this mapping you can see 1 goes to 3, 2 goes to 1, and 3 goes to 2. So in the fourth mapping, let us name this, right? So this is 1, 2, 3, 4, 5, 6. Let us this 1, 2, 3, 4, 5, 6. So in fourth mapping you can see 1 is 1, 1 goes to 1 itself, 2 goes to 3, 3 goes to 2. And again in fourth you can see 2 is fixed, 3 and 1 are interchanged, and 6, 3 is fixed, 1 and 2 are interchanged. This is one way to represent all 6 permutations. This set will be A of S or Sn or S3. So that of all one-to-one mapping between these two sets. And the next thing is, you can represent every permutation as a cycle, right? Every permutation is a cycle. So you can represent every permutation as a cycle, right? You can see I can write this as 1, 2, 3 because this is I, right? This is I. You can see I can write this as 1, 2, 3 alone because you can see 1 goes to 2. I think this is visible or not. So you can see I can write this entire permutation as 1, 2, 3. So if I write 1, 2, this is same as this. You need to read like 1 goes to 2, 2 goes to 3, 3 goes to 1. How I can write like this? I can write this as 1, 3, 2. 1 goes to 3, 3 goes to 2, 2 goes to 1. Right? Here you can see 1 is fixed. If something is fixed, you don't need to write that in cycle. So you just write 2, 3 alone. 2 goes to 3, 3 goes to 2. If some number is missing, you have to imagine that number is fixed. That means 1 goes to 1 itself. I can write this as, here you can see 2 is fixed. So I don't need to write 2. I can write the 1, 3. 1 goes to 3, 3 goes to 1. And here 3 is fixed. So I can just write 1, 2. So this is a cycle representation for a permutation. This is a normal representation. So whenever you have 1, 2, 3, you should imagine this permutation, that is 1 goes to 3, 3 goes to 2, 2 goes to 1. So these are the 6 elements. These are the 6 one-to-one mappings that we can define in a set of 3 elements, right? So therefore we will show that this set forms a group, right? Now, so S3 is I. I means that means 1 goes to 2, 2 goes, that is the same transformation, and it has 1, 2, 3, and it has 1, 3, 2, and it has 2, 3, and it has 1, 3, and it has 1, 2. So these are the 6 elements. So in the beginning I have said Sn as n factorial elements. So this is S3. So it has 3 factorial elements. So it has 6 elements, 1, 2, 3, 4, 5, 6. Now we will show that this set forms a group. So first is closure. So you just take any 2 permutation in S3, you find multiplication. 1 minute. Okay. What is the difference between product and composition? That is very elementary, right? Product means multiplication, composition means composition. That's a 10th standard level. So if we have f1 is equal to x, f2 is equal to sin x, someone is asking what is the difference between composition and product of functions. So what will be my f1 into f2? Let's say this is x square. f1 into f2 is that's a multiplication. It will be x square into sin x. So f1 composite f2 will be f1 of f2 of x. So f1 of f2 of x is sin x, and in f1 you have to replace x by sin x, so it will be sin square x. So you can see both are different. This is x square sin x and this is sin square x, right? Composition products, very elementary. Okay. So these are the 6 elements here. So let us take 2 permutations. Before that we need to know how to composite 2 elements here, right? I'll explain now. So let us take 2 elements. Let A is equal to 1, 2, 3 and B is equal to 2, 3. You can just take any 2 elements. Now we need to find A composite B, that is A star B, that is AB. So far I haven't said how to composite 2 permutations, right? Yes. And now I will explain. So what is AB? It is 1, 2, 3 and this is 2, 3. So you need to find product of 2 elements, that is product of 2 permutations. So what is 1, 2, 3? So after this you write this to this form again, that is this form again. So when you write this form, this will be easy for you to understand. So what is 1, 2, 3? So 1, 2, 3 means 1 goes to 2, 2 goes to 3, 3 goes to 1. And here 1, 2, 3 means 1 is fixed, 3 and 2 are interchanged. Now you just write, we can see 1 goes to 2, move to second permutation, 2 goes to 3, right? 1 goes to 2, 2 goes to 3, 2 goes to 3, 3 goes to 2, 3 goes to 1, here 1 goes to 1. So this is same as 1, 3, 2, right? 1, 3, 2. You can see this element is also in S3. 1, 3, 2 is also in S3. So therefore it is closed, right? So therefore it is closed. 1, 3, 2 belongs to S3. So again, if you take any 2 permutation, the resulting permutation will also be in this. Now A star B is equal to AB. So you can see this is closed. And again associative, right? You can just take any 3 permutation. Similar way, you find A star B star C and A star B star C, you just change the brackets, you will get the same permutation again. And what is the ID element? I is the ID element. So we can also form composition table for this. Now again I is the this permutation is the identity permutation, and sorry this is 1, 3 and this belongs to S3. So therefore this is closed, and similarly you can show identity element also. Now you need to associative again true, ID element is I. So for inverse, let us find inverse. So what will be my B star A? So what will be my B star A? We have 4, A star B is 1, 3. So what will be my B star A? It is 2, 3 and 1, 2, 3. That means 1, 2, 3. 1 3 2 and 1 2 3 2 3 1. So this is 1 2 3, 1 goes to 1, 1 goes to 2, 2 goes to 3, 3 goes to 1, 3 goes to 2, 2 goes to 3. This is 1 2. So you can see that A star B is not same as B star A. So in general this will not be abelian, and also this is not abelian group, this will be group alone because it is not commutative. So product of FG is not same as GF. Okay. So in order to find inverse, so I will give you one trick to find inverse for every element. So suppose if you want to find the inverse for 1 2 3, right, so what you do is you just write this permutation, which is 1 goes to 2, 1 goes to 2, 2 goes to 3, 3 goes to 1. Now what you do is you just again do this, write this transformation again, sorry, permutation again. Now you find product for this. You can see 1 goes to 2, 2 goes to 3, 1 goes to 2, 2 goes, or you can also do like here itself, 1 goes to 2, 2 goes to 3, 2 goes to 3, 3 goes to 1, and 1 3 goes to 1, 1 goes to 2. So therefore 1 3 2 is the inverse for 1 2 3. So therefore inverse for 1 2 3 is 1 3 2. So when you find 1 2 3 into 1 3 2, so this is 1 2 3, 1 goes to 2, 2 goes to 3, 3 goes to 1, and 1 3 2 means 1 goes to 3, 3 goes to 2, 2 goes to 1. So to make a product there, 1 goes to 2, 2 goes to 1, 2 goes to 3, 3 goes to 2. So you can see we have got ID permutation. That means this is the inverse for I. So you can find inverse by just permuting that permutation into itself. So we will get the ID element for every element. So therefore we have showed that the set of all three elements, set of all one-to-one mapping that we can define with three elements forms a group. Now can you find all permutations of S4? So we have 24 elements, so can you find all that? So just take 2 minutes. So just find all one-to-one mapping with the set of 2 elements. So you can either find F1 composite Fg is equal to F2 of F1. I have written F1 composite F2 is equal to F1 of F2. So I have written this because I have thought that function is one-to-one. So you can see z minus z are all one-to-one functions. So therefore I have written straight away like this. You can also use the normal definition, which is F2 composite F1, right? So G composite F, so usually we will define F composite G to be G of f of x, right? So the problem that I did, I straight away did this. So you can, so just for the sake of what I said, we will be in safer side. So just use G of f of x, right? So the example exercise problem that we did, that given exercise problems, consisting of 6 permutations. So just on the safer side, you always use this. F composite G is equal to G of f of x. So just now find all one-to-one mapping that we can define on a set of 4 elements. That is, we are going to find we are going to find all one-to-one mapping in the set of 4 elements. 1, 2, 3, 4. Then we will have 24 permutations, right? So first is ID permutation, and second is 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1, and third is 1 goes to 3, 1 goes 2 goes to 4, 3 goes to 1, 4 goes to 2, and third is 1 goes to 4, 2 goes to 1, 3 goes to 2, and 4 goes to 3, and fourth is you need to fix 1 and you permute 2, 3, 4. So you will have 2 permutations here, and you fix 3 and permute 1, 2, 4, again you will have 2, you fix 3, you permute 1, 2, 4, so overall you will have 24 elements. So I write all 24 elements alone as a cycles. Okay, let's write all the elements. So this set S4 contains I and 1, 2, 1, 2, 1, 3, 1, 4, 2, 3, 1, 3, 1, 4, 2, 3, 1, 2, 3, 4, 2, 3, 2, 4, 3, 4, 2, 4, 3, 4, and 1, 2, 3, 1, 3, 2, 1, 2, 3, 1, 3, 2, 1, 2, 4, 1, 4, 2, 1, 2, 4, 1, 4, 2, 1, 2, 3, 4, 5, 1, 4, 2, 1, 3, 4, and 1, 3, 4, 1, 4, 3, 2, 3, 4, 1, 4, 3, 2, 3, 4, 2, 4, 3, 1, 2, 3, 4, 1, 2, 3, 4, and 2, 3, 1, 4, 3, 1, 2, 4, 1, 2, 3, 4, 1, 2, 4, 3, 1, 3, 2, 4, and 1, 3, 4, 2, 1, 4, 2, 3, 1, 4, 3, 2. So these are the 24 permutations, right? You can easily draw this by diagram, right? The first is ID permutation. The second is 1, 2, 3, 4, 1, 2, 3, 4. Here we have 3 and 4 are fixed. So here we are just transforming 1 and 2. So we have this, and if you fix 2 and 4, you will have this. If you fix 2 and 3, you will have this. If you fix 1 and 4, you will have this. And if you fix 1 and 3, you will have this, and if you fix 2 and 1, you will have this. Now I am fixing, here I am fixing 2 elements and permutating 2 elements. You can see I am fixing two elements, I am permutating another 2 elements. Now I am going to fix 1 element. So for all these, I am going to fix 1 element. So we have 3 possible permutations. So for example, you can see I am fixing 4 here. So if I am fixing 4, 1, 2, 3, 4, and this will be 1, 2, 3, 4. So what are the permutation I can define here? So I have 2, which is 1 goes to 2. So you just think of this as F3 now. 1 goes to 2, 2 goes to 3, 3 goes to 1, this is 1, and 1 goes 1 2 3, 1 2 3, 4 is fixed, so I can go 1 2 3, 2 to 1, 3 to 2. So I can define 1 2 3 and 1 3 2. If I fix 4, and again you fix 3, you will have these 2. You fix 2, you will have this 2. You fix 1, you will have this 2. So these 1 2 3 4 5 6 elements are obtained by fixing 2 elements. Another 6 elements are obtained by fixing 1 element. Now I am going to multiply these 2, or I am going to, what I am going to do is, so 1 2 3 4, 1 2 3 4 is just 2 2. So 1 and 2, 3 and 4. Again 2 and 3, 1 2 3 4. Now 2 3 3 2. Again 4 1 1 4. From this you will have 1 2 3, 2 permutations, and here this is normal, right? So we are just moving one step. So 1 goes to 2, we are moving one step. 1 goes to 2, 2 goes to 3, 3 goes to 1, 4 goes to 2. So you will have this permutation, and if you move 2 steps, you will have this permutation. You move 4 steps, you will have this permutation. Similarly, you will have 8 permutations here, right? So these are the 24 permutations that we can define in a set of 4 symbols, that is 4 elements. So let me write S3 also. So S3, this is I, then we got 1 2 3, then we got 1 3 2, and we got 1 1 2 1 2 2 3 3 1 1 2 2 3 3 1. So these are 6 elements in S3, and these are 24 elements in S4. And in S5, if you find, it will take so much time, which is 5 factorial. So we have 120 permutations in S5, right? So if you want to try, you can try, but this won't be as an exam. So it is not possible for us to write all 120 permutations in 5 or 10 minutes. So we will just consider these 2, right? Remember, just practice these 2 permutations, because you will be using lots of results from this. So whatever concept you study, either normal, subgroup, or order of an element, whatever concept, this will serve as an example, right? So just memorize all the elements also, right? These 24 elements and these 6 elements. Now we are going to define 2 terms. Now we are going to define 2 terms. We will be introducing, I am going to introduce some notations or some terms. So first definition that we are going to see is transpositions. So you can see every permutation is represented in a cycle. Every permutation is represented in cycle. If you have to prove it is not abelian, then commutative will be enough. Yes. If you have to prove commutative, first you have to show it is a group. Then you have to prove that it is not abelian. So these are the notations. Now you can see I have expressed every permutation as cycles. So you can see this cycle length is 1, because we have only one cycle. This cycle is length 1, this cycle is length 1, this cycle is length 1. You can see this cycle is length 2. So we have 2 cycles. So this permutation is cycle length is 2. This permutation cycle length is 2. This permutation cycle length is, okay. So we have 2 permutations of cycle length 2. Okay. So now we will define the term transpositions. A cycle of length 2 is called transposition. So now define transposition. A cycle of length 2 is called transposition. Can see these 2 are transpositions. So this cycle length is 2. So a cycle of length 2 is called a transposition. So this is the first definition that we are going to see. So we have verified that in general S3 is not abelian. So let me give you one more result. So the result is if F and G are two disjoint cycles, then it will be commutative. So for example F3, I have taken these two permutations, right? So I think I have taken some. Suppose if I think I have taken this permutation, so you can see if you take whatever permutation you take, you can see these two cycles are not disjoint because 2 is here and 3 is also there, right? Again when you take these two, again it is not disjoint because 1 and 1 are here. If one element is present also, it is not disjoint. And whatever two cycles you take, so whatever cycle you take, it will surely not be disjoint, right? Suppose if you take this and this, it is not disjoint. If you take this and this is not disjoint. So that is why only we are not getting commutative for S3. But I am going to quote one result. Suppose if the cycles are disjoint, then it is commutative, right? Suppose if the cycles are disjoint. For example, let us take 1 2 and 1 2 3 4. Now let us take these two. We can see these two cycles are disjoint. Now we will find 1 2 3 4 and 1 3 2 4. So 1 2 3 4. So what will be this permutation? So 1 2 3 4. 1 2 3 4. So 1 goes to 2, 2 goes to 1, 3 and 4 are fixed. Here 1 2 and 1 are fixed. Sorry, 1 and 2 are fixed. 3 goes to 4, 4 goes to 3. So what will be my product of these two permutations? 1 goes to 2, 2 goes to 2, 2 goes to 1, 1 goes to 1, 3 goes to 3, 3 goes to 4, 4 goes to 4, 4 goes to 3. So we have 2 1 4 3. Now we will find 3 4 and 1 2. I'm just finding 1 2 and 3 4, and I'm just finding 3 4 and 2 4. So this is 1 2 3 4, 1 2 3 4. So here 1 and 2 are fixed. This is 4 3, and here 3 and 4 are fixed. This is 2 1. So here this is 1 2 3 4. 1 goes to 1, 1 goes to 2, 2 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 4 again. You can see 3 goes to 4, 4 goes to 4 again, 4 goes to 3, 3 goes to 3. Now you can see both are same. So what we can conclude is, if the cycles are disjoint, then it is commutative. But here in S3 you cannot find two cycles that are disjoint. But S4 is not abelian. Remember very carefully. If every cycle is disjoint only, then entire group will be abelian, because if a group have to be abelian, every element has to be commutative. But here I can find two cycles which are not disjoint. For example 1 2 1 1 4. So if I found product of this into this and this into this will not be equal. So if every element is equal only, then we say the group is abelian. So what we can conclude is Sn is non-abelian. Sn is non-abelian for n is greater than or equal to 3. If n is equal to 2, it will be abelian. If n is equal to 2, we will have only two elements, right? For example S2, so we will have only two permutation. So 1 2 1 2, 1 goes to 2, 2 goes to 1, and in S3 1 goes to 2, 2 goes to 1. So this is I and this is 1 2, and we know that a group of order prime is always abelian. So we will discuss that later. So since 2 is a prime, a group of order less than or equal to 5 will always be abelian. right? So you can see 2 is less than or equal to 5, so it will be always abelian. So you can see S3 is ordered 6 and S4 is ordered 24. So you know transposition, your cycle of length 2 is transposition, and the permutation will be commute if the 2 cycles are disjoint. So these are the 2 results that we see now, and you know how to find inverse, right? Yes. Now we are going to do third result. Every permutation can be expressed as a product of disjoint cycles. Every permutation can be expressed as a product of disjoint cycles. That is what I have expressed, right? So every permutation can be expressed as a product of disjoint cycles. This is very important. Every cycle can be expressed as a product of transposition. So first result is we have seen transposition, a cycle of length 2 is transposition. Second result is 2 permutations commute if the cycles are disjoint. Now third result what we are going to see is every permutation, so I will erase this off. The third result is every permutation can be expressed, as a product of transposition, as a product of transpositions in infinitely many ways. So every permutation can be represented as a product of transpositions. For example, for n cycle, so for n cycle A1, A2, A1, A2, A3 up to An. So we can represent this cycle as a product of transposition by A1, A1, A2, A1, A2, A1, A3. You can see it's a transposition. You can see cycle of length 2, right? So length 2, 1, 2, 1, 3, A1, A4 up to A1, An. So in this way we can represent every permutation as a product of transposition. Both are same, you can verify that. So I will give you one example also. So consider so for example, let us consider 1, 2, 3, 4, right? This is one permutation in S4. So we can write this as a product of transposition by 1, 2, 1, 3, 1, 4. Both are same, right? So we can see every permutation, every cycle can be expressed as a product of transpositions, right? Transpositions. Okay. So we have defined transposition, we have defined disjoint cycles, so we have defined inverse, we have defined this result also. Okay. Now again, for example, you can also represent 1, 2, 3. 1 2 3 as 1 2 and 1 3, 1 2 and 1 3. So we can also represent 1 2 3 as 1 2 1 3, 1 2 1 3, right. Now we are going to introduce another two definitions. So from this what we infer is every cycle can be expressed as some product of transpositions. So you can see S3 now can be written as, so instead of 1 2 3, I can write 1 2 1 3, and instead of 1 3 2 I can write 1 2, this 1 3 2, 1 3 2, 1 3 1 2. So I can write 1 3 1 2. So from this result I can write every cycle as product of transpositions. Now we are going to define two definitions. Again in S4 also you just take any cycle, you can represent any cycle as a product of transpositions, and also you can verify that both are same. You just find 1 3 1 2, you will get same 1 3 2, right. Even permutation, we are going to define term even permutation. So for example, in S4 we will have some elements like this. So what is this cycle representation? I can represent this as a product of transpositions by 1 2 1 3 1 4. Now we can see how many transpositions are there. 1 2 3. I have expressed this cycle as product of 3 transpositions. Now how many transpositions are there? I have expressed this cycle as product of 2 transpositions. I have expressed this cycle as also product of 2 transpositions, right. So you can see if the number is even, then this permutation is called even permutation. If the number is odd, then it is called odd permutation. Very easy. If the number of transpositions is even, then it is called even permutation. We can see this even permutation. Why? Because when I write this as a product of transposition, I will have 2 transpositions, number to 2 even. But this is not even permutation. When I write this as a product of transposition, I have 3 transpositions, which is odd number. So it is not a even permutation. So we will define even permutation, odd permutation. A permutation is said to be even permutation. A permutation is said to be even permutation. Even permutation if it can be expressed as, a permutation is said to be even permutation if it can be expressed as product of even number of permutation. Product of even number of permutation. If it can be expressed as product of even, this is not even permutation. You can see this is a product of only one is odd number. This is not even, but these two are even, right. These two are even. Why? Because I can express this as a product of even number of transpositions. Even number of transpositions. Otherwise it is said to be odd permutation. Otherwise it is said to be odd permutation. So now can we find all even permutations of S3 now, right? Now we will find all even permutations of S3. Now I am going to call a new group, right? So I am going to call all even permutation will form a group, right? All even permutation forms a group, and that group is called alternating group, right? So we will discuss that very soon. So before that we will find all even permutations of S3. So S3 is 1 2 3 1 3 2 1 2 1 3 1 is 3 and 2 is fixed, here 3 is fixed, here 2 3 is fixed, 2 is fixed, 1 is fixed, so 2 3. So I can write this as 1 2 1 3. Can write this as 1 3 1 2. Even identity permutation is always even permutation. Identity permutation is always even permutation. Identity permutation is always even permutation. So so I can how I can represent ID permutation? I can represent ID permutation as for example I can represent this as 1 2 3 3 2 1 1 2 3 3 2 1. I can represent I as 1 2 3 3 2 1 1 2 3 and 3 2 1. So we can see what is 1 2 3. 1 goes to 2, 2 goes to 1, 2 goes to 3, 3 goes to 2 again, 3 goes to 1, 1 goes to 3 again. So I can represent an ID permutation as 1 2 3 3 2 1. And again I can write this as product of transpositions 1 2 1 3 3 2 3 1. Right. So in this way I can write every permutation like this. So you can see there are 4 transpositions which is even permutation. So therefore ID permutation is always even permutation for any S4, S5. ID permutation is always even permutation. So I am going to call I am going to group all the even permutation in one set. All even permutation in one set. So 1 2 1 3 and 1 3 1 2. I am going to call this as A3. So A3 means alternating group on 3 symbols, that is the set of all even permutations on S3. Set of all even permutations on S3. Right? Set of all even permutations on S3. We are going to call this will be a group. This will be a group. Set of all odd permutation will not be a group. Why? Set of all. So I collected in out of 6 elements. I have collected the elements that are even permutation. So we have 3 elements here. So we have another 3 elements which are not even. So therefore these 3 are odd permutations. These 3 are odd permutations. So a set of all odd permutations is not a group. Why? Because it does not have ID element. Right? Because ID permutation have to be in a group, then only it will be a group. So therefore the set of all odd permutation does not have ID element, so it will not form a group. So set of all even permutation will form a group, and we are going to call that as A3. Now we can see how many elements here. We have 3 elements. How many elements in S3? We have 6 elements. So in general the number of elements in AN will be n factorial by 2. Important result. The number of elements in AN, that is set of all even permutations, will be number of elements in S3, that is n factorial by 2. So we have 6, we have 3. Now can you find all even permutations of S4? Now can you find all even permutations of S4? You take this exercise, right? So you find all even permutations of S4. So I already listed all 24 elements. Now you write every cycle as a product of transpositions, and if the number of transpositions is even, you collect that in a separate set, and you will have 12 elements in A4, right? A4. So I'm giving you exercise to find all the elements of A4. Now we will do problems. So I think you can write all the permutations on A4, right? If you want, also you can write, and you just you can see this cycle is length 1, this cycle is length 2. So cycle of length 1 will always be even permutation. The cycle of length 1 it will always be even permutation, because if I have a length 1, okay, and we will not the result later on. So you just write every permutation as a product of transposition, and if the number of transpositions is even, you collect that in a separate set, you just form A4. So if you want, I can also write the elements of A4 now. Okay, I will write the set of all even permutation in S4. So A4 is set of all even permutations in S4. So surely it will have I, and 1 2 3 1 3 2 1 2 3 1 3 2 and 1 2 4 1 4 2 1 2 4 1 4 2 1 2 4 1 4 2 1 3 4 1 4 3 1 3 4 1 4 3 2 3 4 2 4 3 2 3 4 2 4 3 2 1 2 3 4 and 2 3 1 4 and last is 3 1 2 4. So these are the 12 even permutations in S3. You can see this I can write as 1 2 1 3. So we have even number of transpositions 1 3 1 2 2 1 2 2 4, sorry, 1 2 1 4 1 4 1 2 1 3 1 4 1 4 1 3. You can see already it has 2 transpositions. So these are the 12 permutations that are even in S4. So you are going to call that as S4. So you can see in general number of elements in AN will be n factorial by 2. Now we will do some problems. So write the following permutation as product of disjoint cycle. Write there. This is important UPSC question. Write the following permutation as a product of disjoint cycle. So we need to write that permutation as a product of disjoint cycle. So the first question is 1 2 3 4 5 6 7 8 9 2 3 4 5 1 2 3 4 5 1 2 3 4 5 1 6 7 9 8. Now we can easily write this, right? So this is a permutation. So we know how to write this as a cycle, right? You can see 6 is fixed, 7 is fixed, and you can see 8 and 9 are transforming here, and 1 goes to, I can write this as 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. So we are starting with 1 and we are ending with 1. So you just close the cycle, right? You just close the cycle. 6 7 7 is fixed. So don't need to write that permutation. 8 and 9 are reversed. That's it. Right? So you need to stop until you get 1. You can see 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1 again. That means we are getting the same element back again. So you just close the cycle. Now you just form another cycle. So 6 and 7 are fixed. So you don't need to write that in cycle. So 8 and 9 are reversed. So therefore 8 10. That's it. This question is asking 6 marks. So B, second problem. So 1 2 3 4 5 6. 6 5 4 3 1 2. 6 5 4 3 1 2. Now start with 1. 1 goes to 6. 6 goes to 2. 2 goes to 5. 5 goes to 1. So we have 1 again. So just close the cycle. Right? And you can see 3 and 4 are transpositions. That's it. Right? Start with 1. 1 goes to 6. 6 goes to 2. That means 6 2. 2 goes to 5. 5 goes to 1 again. So just close the cycle. Now you go for another transition. You can see 3 and 4 are reversed. Therefore 3 4. That's it. So we can represent any transposition as a product of disjoint cycles. So we will do some exercise problems. So decompose the following permutation into transpositions. So second is decompose. So this, if you have any doubt here, you can ask. So we have just represented this permutation as a product of disjoint cycle. A permutation is said to be abelian if all disjoint cycles. Yeah, we don't need to, actually there is no result like that. We don't do like that, right? Actually it is true, but there is no proof like that. Okay, so now we move on to the next problem. Now decompose the following permutation transposition. Decompose the following permutation into transposition. So we need to write this as transpositions, product of transpositions. Now first, and check whether it is even or odd, and check whether it is even or odd, and check whether it is even or odd. So first is 1 2 3 4 5 6 7, 1 2 3 4 5 6 7, and 6 5 2 4 3, 6 5 2 4 3, 6 5 2 4 3 1 7. So first we need to represent this as a product of transpositions. Before that we will first express this as a product of cycle, and from cycle we know how to express the process of transpositions, and then we will count the number of transpositions. Depending on that we will say whether it is even or odd. So you can see 4 is fixed, 4 is fixed, 7 is fixed. So we don't need to write 4 and 7 in first we will write this as disjoint cycles. So 1 goes to 6, 6 goes to 1 again. So we need to close the brackets, and 2 goes to 5, 5 goes to 3, 6 5 2 4 3 1 7. Yes. So 1 goes to 6, 6 goes to 1, and 2 goes to 5, 2 goes to 5, 5 goes to 3, 3 goes to 2 again, 2 goes to 5, 5 goes to 3, 3 goes to 2 again. So that means we need to close that. We have 2, so we need to close, strike out and close that, and that's it, right? So 4 and 7 we should not write because that is fixed. So this is the disjoint cycle, and we know this disjoint cycle can be written as product of transposition. So we know how to write this, right? So 2 5 2 3, right? 2 5 2 3. So how many transpositions are there? 3 transpositions. That means it is odd permutation. So check whether it is even or odd. So it is odd permutation. So now we'll move on to second problem. So first you represent that, suppose in the exam it asks us to find whether permutation is even or odd. You first write that as a cycle, and from the cycle you can shift that to transpositions and count the transposition. So now we'll move on to the next problem. So 1 2 3 4 5 6 7 8, 1 2 3 4 5 6 7 8, 3 1 4 7 2, 3 1 4 7 2, 5 8 6. Now none of the elements are fixed here. Okay, so first we will start with 1. 1 goes to 3, 3 goes to 4, 4 goes to 7, 7 goes to 8, 8 goes to 6, 6 goes to 5, 6 goes to 5, 5 goes to 2, 2 goes to 1. You need to close that. So already we have 8 elements, 1 2 3 4 5 6, 1 2 3 4, sorry, we don't need to write 1. This is the disjoint cycle. So we have only one cycle. Now you write this as transpositions. So you know how to write transpositions, right? 1 3 1 4 1 3 1 4 1 7 1 8 1 6 1 5 1 2 and 1 2 3 4 5 6 7. So again it is odd permutation. So determine which of the following are even permutation. So third problem. Determine which are even. You take this exercise. The first problem is 1 2 3 1 2 3 1 2. B is 1 2 3 4 5 1 2 3 4 5. They are given cycles 1 2 3 4 5. And C is 1 2 1 3 1 4 2 5 1 2 1 2 1 3 1 2 1 3 1 4 2 5. Now you can see it is clearly even permutation. Transpositions, 4 transpositions. Here this is odd because you can represent this as 1 2 1 3 1 2. So we have only 3. So this is odd, and this I can write this as 1 2 1 3 1 4 1 5. So we have 4 transpositions here. And here we can write this as 1 2 1 3. This is 1. So already we have 7. So this is also odd, and this is even. So we have 4 transpositions. So you just represent this as a transposition. So we have 1 2 1 3 1 4 1 5. So we have 4 transpositions here. And again we have 2 here, 1 2 1 3. Again this 1. So when you add up you will have 7. 7 is odd number. So therefore this is odd permutation. So this is the only one which is even. Find the inverse of the following permutation. Find the inverse of following permutation. First is 1 2 3 4 1 3 4 2. Second is 1 2 3 4 1 3 4 2 1 2 3 4 3 4 1 2. And fourth is 2 3 1 5 4 2 3 1 5 4 2 3 1 5 4 1 2 3 4 5. So to find inverse, you just permute with the same 1 2 3 4 1 3 4 2. So if you do this 1 2 3 4, 1 goes to 1, 1 goes to 1, 2 goes to 3, 3 goes to 4, 3 goes to 4, 4 goes to 2, 4 goes to 2, 2 goes to 3 again. So this is the inverse. To find inverse, you just do that with same permutation, right? Product with same permutation.